So hi everyone, and welcome to Rasa's office. We're really happy that it's actually like not fit, like you can't really fit here. That means like our meetup is growing. This is our 5th meetup, deep tech meetup, and we're really happy to see some new faces. Who is here for the first time? Nice. Okay, cool. So you're in for a treat. We just flew in 2 great speakers, one from Copenhagen and the other one just came from Cambridge, and they're gonna give you a very technical talk today, so I hope you're prepared. I also hope that you have prepared some questions. Both of them are going to be talking for around 20 minutes, and then you'll have time for 2-3 questions. If you don't get to ask your question, just like we'll have a networking part after it, so you can just grab them and like ask them. Yeah, I mean, I would just give the stage to Yova, and yeah.
Okay. Hi everyone. I'm very happy to be giving a talk for the first time in front of an industry audience, actually. This is a new experience for me, and I hope I do okay. I'll be very happy to hear your thoughts on the level of detail and yeah, just the general style at the end of the talk. But I hope this is as interesting for you as it is for me. So I'm currently doing a PhD in NLP and machine learning at the University of Copenhagen. I'm in my 2nd year, and so far I've mostly been working on the topic of cross-lingual embedding alignment. And I would imagine that many of you have no clue what that's about. So the title has the word basic in it, just to let you know that I'm not going to go very deep, but I'm going to try to give you a good idea of what the task is and how we solve it. Right, so the overview of the talk goes like this. I'm going to tell you what cross-lingual embedding alignment is. I'll try to give you a pretty detailed idea of how we obtain an alignment with supervision. I'll tell you that what we're currently doing isn't working so well, but when is that ever a surprise in NLP? And lastly, I'll just give you some hints about what lies beyond the scope of today's talk, just in case you decide to go further into this topic. Okay, I hope nobody here is offended that I'm going to spend 2 minutes talking about what word embeddings are. I just want to make sure that we're all on the same page here. So in NLP, we work with language. Language comes in the form of words, and words are discrete entities. But we want to be able to do algorithmic computations over them, so we need some sort of a numeric representation. And usually that's a vector that represents in some way the semantics and syntax of words. So word embeddings are these dense vectors that you can imagine sort of, if they were in 2 dimensions, looking something like this, where the words for car, bike, and truck would like close together. Their absolute location is meaningless, but their relative location, the fact that these 3 words, which all refer to some sort of vehicles, like close together, that's what we want to capture with embeddings. Their semantic similarity word they, which is not related to vehicles, and that's why it's somewhere further away in space. And one common thing we would do with word embeddings with these vectors is we would take their dot product and compare the dot products of different pairs of words, for example, in order to get a feeling for which words are more similar. And in this completely made-up example, surprisingly, the dot product of car and bike is higher than the dot product of car and they. And this is in line with our intuition that car and bike are more similar semantically than car. See some nods, we're good. This is what word embeddings are. And now switching the focus to cross-lingual word embeddings. It's not very different. The only distinction is that in cross-lingual word embedding spaces, we represent the vocabulary not just of a single language, but of 2 languages, for example, or 3 or whatever. But sticking just to 2 languages for now, the idea is to have an embedding space where the embedding of the word car would lie somewhere close to the embedding of the word coche, which is Spanish for car. And that's about it. The reason we want to have such cross-lingual embedding spaces is mostly for transfer learning purposes. So very often in NLP, we would have label data for one language, or we would have more label data for one language than another. And then it's nice to have we can obtain from the label data in English, for example, to some unlabeled data in Spanish. And one example here, just a toy thingy. If we have a function f that we've learned on the embedding of car, that maps car into label y1 and maps day into label y2, we might want to see that when we give the embedding for the word coche to this function, it would also map into label y1. I hope this makes sense. Okay, and now on to the alignment part of cross-lingual embedding spaces. So historically, cross-lingual embedding spaces have been learned from parallel data, because naturally when you want a space that represents the semantics of two languages similar way, you would want to start off or to learn this space from parallel similar data. But as you probably know, monolingual data is always available in far bigger quantities than parallel data, which is why we want to be able to utilize this somehow, the monolingual data itself. And for the last couple of years, people have been putting a lot of effort into trying to learn, or well, trying, it's not so hard, into learning monolingual embedding spaces and trying to align them to obtain a cross-lingual embedding space. And this is what today's talk is about. Okay, how do we do supervised alignment? So we have our English embedding space on one side, our Spanish embedding space on the other. If you imagine how these spaces are positioned right now, obviously the embedding for the word car is nowhere near the embedding for the word coche, and this is what we want. And even if we were to take the two spaces and just overlay them on top of each other, this goal is still not achieved. So we need to do something a bit more complex, and what we would actually do is take a training dictionary of gold standard word pairs such as car, coche, truck, camión, bike, bicicleta, and we're going to use the knowledge that the embeddings of these particular words have to be aligned in order to obtain some notion about how the overall spaces have to align. So we'll actually subspaces defined by the training dictionary, or rather we'll only be looking at the words that are in our training dictionary while learning the alignment. Okay, and here's my cool animation of what we want to do. I hope you appreciated that. Yeah, okay, so this is where we want to get. And the way we'll try and achieve that is using point set matching. So I intentionally tried to make this imperfect because it really isn't the case that we can achieve a perfect alignment between the languages, but this is very close to where we want to get. Okay, so what is point set matching, or how do we match point sets? So this is a different view kind of on our data. Before I showed you the visual representation of the embeddings sort of in a Euclidean space, and now we're actually looking just at the vectors themselves. And we're going to be, like I said, working with subsets of the entire embedding spaces defined by the words in our dictionary. So here we have two matrices, X prime and Z prime, where each row of the matrices is sort of aligned in the sense that the first row of X prime contains the embedding for car, the first row of Z prime contains the embedding of coche, and these two are translations of each other. So these are the matrices that we'll be working with, and what we want to learn as a product of or as a way of solving the task of the alignment is another matrix, W, which belongs to dimensions matching the dimensions of our embeddings. And what W needs to give us when multiplied with X prime is Z prime. A little note about the primes. This is just to remind you that these are subspaces from the entire embedding spaces. So yeah, W is this matrix that we want. For example, if we multiply the first row of X prime with W, we want to obtain the first row of Z prime. This is the objective. Okay, little note about W itself. So because it's just a matrix, you might be getting a feeling for what kind of alignment we're doing. It is restricted to be a linear alignment. And the reason a lot of work in this area has restricted itself to linear alignments is this cognitive science paper from a few decades ago that says the semantic spaces of speakers of different languages, the semantic graph sort of that we all have in our heads, regardless of our native language. I see some confusion, but if you're not a cog-sci person or you're not into linguistics, just trust me. Somebody out there said, no matter what our native language is, we're supposed to all conceptualize the world in fairly similar terms. And so if we then think of word embedding spaces, if we're willing to make the assumption that word embedding spaces reflect the semantic graphs that we have in our heads, then we can deduce that word embedding spaces should also have underlyingly similar structure regardless of the language that particular. And then by extension, this means that we should be able to align them in linear terms. Okay, you don't have to understand this because in a few minutes I'll tell you I don't believe in it, but yeah, that's okay. But this is the assumption that underlies a lot of work in the area from the last couple of years. Okay, so let's agree for a moment that W is going to be, that the mapping is going to be just a linear matrix W, and this is what we want to learn. And our training objective is that the product of X prime W should lie as closely to Z prime as possible. So we want to minimize the distance between the transformed, let's call X the source space, English, let's call it the source space. So the transformed source space should lie as closely as possible to the target space. And very conveniently, there is a closed form solution to this problem, which might explain why people decide to stick to linear alignments. Because how cool is it that you don't have to do gradient descent and risk finding a local minimum and all that? So the closed form solution is Procrustes analysis, which tells us that if we take the product of the two subspaces Z prime and X prime, and we apply singular value decomposition to that, the product of two of the resulting matrices V and U gives us W. That's it, basically. This is what we do. And I don't even have any code to show you how it's done because it's 4 lines of code, literally. Okay, a little note on one alternative that I actually published a paper about. So in Procrustes analysis, we map the source space directly onto the target space with this one matrix W. In an alternative approach called generalized Procrustes analysis, we would induce a third latent space, which is simply the mean of the source and target space. And we would learn 2 mappings, one from the source space into the latent space, one from the target space into the latent space. And very conveniently, this seems to give us slightly better solutions. Slightly better, you know, meaning not revolutionary, but if you're interested to hear more about this, I could main part of the talk. Okay, so let's assume that we've obtained a solution using either Procrustes analysis, generalized Procrustes analysis. We've aligned the words in our test dictionary. And now we want to figure out how well does this alignment clearly learned on a set generalized to the entire embedding spaces. And the way to go about this usually is this intrinsic evaluation method called bilingual dictionary induction, where we would use some held out word pairs that we know are correct matchings between the two languages, such as nadar, meaning swim in English. And we would actually query our space in the following way. So if we, for example, know that this is the embedding of nadar, we would check whether its nearest neighbor is the embedding of swim. And if that's the case, we would say, okay, my precision at 1 for this particular word pair is 1. And nearest neighbor is the simplest technique to use for this. There are other more complex approaches, but I don't think we need to go into them. But the assumption is that for a lot of the pairs that are outside of our training dictionary now, the alignment will hold just as well as it does for the training dictionary itself. Okay, so I already spoiled it that this is not going to go so well. Here's a diagram of the precision at 1 we get for a bunch of different alignments between English and different target languages. And this is actually the training fit. So here I'm not even telling you it doesn't generalize well. This is just to give you an idea of how well the training data itself can be fitted by the model. And okay, up here we have English aligning to English. Not very interesting. Oh, I don't have a pointer. Okay. But then, okay, English to Spanish, English to Portuguese, English to French. These are all in this range of 85+% precision. This is almost promising, and it is something that people have been able to use for downstream tasks and actually achieve something. But you can see that there is a very steady decrease in the curve as we go left, all the way down to languages like Latvian and Lithuanian scoring at about 50%, Chinese and Tamil 40-something, and then I don't even know what's going on with Japanese. I still, like, I've had this plot for a few months now. I still haven't looked into it exactly, but you know, you can see that there's something very wrong there. Okay, so why is this the case? Why can we align English to Spanish and Portuguese well, but it's not really as good all across the board? Well, there are several problems with this approach, both with the approach itself and the assumptions that it makes. So the accuracy of the monolingual embeddings themselves is obviously going to be a crucial part, is going to play a crucial part in the success, because we rely on the chain of assumptions that monolingual embedding spaces represent semantic spaces. Semantic spaces are supposed to be alignable between, or rather to have underlyingly a similar structure and so on. But in practice, when we don't have the appropriate, the sufficient amounts of data, none of these assumptions can even dream to hold. Look back at this plot. This could be a very good explanation for Latvian, Lithuanian, Bosnian, all of these languages. So I should say often we use fast text embeddings trained on Wikipedia data for these experiments. And Wikipedia for Bosnian is just not that big. You really cannot hope to learn very good representations for words from insufficient amounts of data. And then another problem we have, which is sort of entangled with the amounts of data, but also a problem in itself, is the linguistic properties of languages. So languages with a very different morphosyntax could hardly have a very similar structure underlyingly, simply due to the fact that a single word in English would map to 6 different words in Spanish, for example. And then it's just hard to imagine how a linear alignment in itself would be sufficient to capture correspondences between these languages. This is something that very few people have looked at so far. I'm trying to do some work in the space, but it's hard. It's like saying that a linear alignment is insufficient is easy. Saying what should work better and actually showing that it works better is trickier. And then lastly, if you end up doing any of this, don't trust the test dictionaries. They're full of proper names, they're full of gaps, there's just so much noise in there. Okay, and then one last slide just to give you an idea of, yeah, if you end up being interested in this, you end up doing anything with it. These are a couple of things to keep in mind. So the bilingual dictionary inductions course, the intrinsic evaluation task that I talked about, it's now been shown to not correlate very well with actual transfer learning potential. So depending on what your objective is, you might want to consider doing extrinsic evaluation. If your ultimate goal is to get a bilingual dictionary, then sure, look at the performance in terms of BDI, but if you're actually considering doing some multilingual learning through transfer, then just do the extrinsic evaluation. And then another note, so my main interest is really in the question of, is a linear mapping the best we can do? Or if not, what else is there to be done? Which is why I've restrained myself. But there are unsupervised methods to cross-lingual embedding alignment as well. And if you want to hear more about this, my colleague Marijke Hartman, Alan, this one is for you, is very, very proficient in the topic. So yeah, you should, it's really an interesting topic. It has completely different problems from what I'm working on, but it's really worth exploring as well. And I'll close this talk on a slide that just gives you an idea of what are the best frameworks out there, the best code bases for this kind of work. They're all super easy to use, not always very straightforward to read and change and so on, but if you just have some data that you want to play around with, if you have an idea for how any of this could be relevant to your work, these would be the places to go to. And then the papers that I've based this talk on are also cited in the readmes of all of these GitHub repos. So yeah, that's it. Thank you very much.
So does anybody have a question?
Right.
I have two questions, but I'm just going to ask one for now.
Okay.
Do you think the dimension of the embedding plays a big role? Like, to do a three-dimensional, 10-dimensional, 1,000-dimensional embedding, depending on, and do the same technique with higher dimensional embeddings, and does that?
Oh, I should say I was giving examples with two-dimensional data just for the sake of easy visualization. In reality, we work with embeddings in 100 or 300 dimensions or something like that. Yeah, I don't think anyone would be interested in embeddings of 2 dimensions.
Then I do ask the other question. So, do you think it would be possible to, instead of trying to map words to each other, mapping the underlying concepts to each other, because they should be the same? So first have a step where you translate word to concept, and then translate to the and then concept back to word in the other language, basically.
Yes, that's definitely one way to go about dealing with the morphosyntactic differences in language. But to the extent that data sparsity and morphosyntactic differences are the two main issues at the moment, trying something like that would actually, I think, increase the demands on the data that you need. So then there's a bit of a trade-off there. But it is something like, even just lemmatizing the data is something that people have tried, and it has its benefits, yeah. Any other questions? Okay, where should I, okay, Alan?
So it seems very plausible that the fact that you can't get zero error on the training data is because of morphology just being different, especially if you're starting with English and then you're comparing to other languages. But then maybe if you looked at the 10 or 20% that just don't align, and like, are those inflections? Like, is there a systematic thing that you can't fit that you can look at?
Okay, so this is how we actually ended up looking into the quality of the evaluation technique. And it turns out that, so the plot that I showed is based on the original test dictionaries. We recently submitted a paper where we release cleaned data sets kind of for a few of the languages, but we don't have them for all of them. So definitely part of that gap that you see there is just based on missing inflections, even from the test dictionaries itself. one of the more systematic issues that we see is collapse between synonyms and antonyms, for example. And then some of it is just slight semantic differences between languages, because even if you have a perfect overlap in morphosyntax, it just is a matter of fact that different languages conceptualize the world in slightly different terms. And then that ends up giving you some misalignments as well. Yeah, I have a question there.
Have you tried doing within, I think the last one you were showing between languages, but have you ever tried, because you said that the sparsity of data, using a single language and doing the same thing with a single language trained on two different corpuses, corpi, which might be domain specific, to see how much effect you get from the corpus, because both of them are going to have the same morphosyntactic problems.
Yes, yeah, there is work on that actually from my supervisor, but prior to me joining the group, that shows that the domain plays a huge role, which is also why we think that for some languages, even if you have stable amounts of data in Wikipedia, for example, it just happens to be that different cultures would write articles on Wikipedia on different topics. And then even though we make the assumption that Wikipedia is a consistent domain across languages, that's yet another.
Within Wikipedia, though, because you can go, they may have some articles missing to kind of create a less biased cross-language version. Like have each language broken up into different domain modules, and then.
Yeah, I suppose because sort of linking between articles, and then you could probably parallelize your data sort of by checking away all the articles that don't match between the two languages.
But it hasn't been done.
No, not that I know of. A question here? Or?
Oh, I was kind of asking about the, depending on the base language you're using, but you kind of answered that with the domain makes a big difference.
Okay, yeah.
Cool, so no, we're gonna wrap this up. Sorry, we can have a few questions after that. And yeah, thank you so much.
Thank you.
I'll tell you a bit about today's topic. As I was saying, language modeling basically allows us to estimate probabilities. I give you some examples here in English. And basically, you can easily understand how important it is to discriminate between correct word orders. So for example, in English, we would say that the sequence rabbits like carrots has a higher probability compared to like rabbits carrots. At the same time, we have a sort of semantical nuance to the task, which means that we want to basically assign higher probabilities to sequences like rabbits like carrots compared to rabbits surmise carrots. Basically, this means that we can learn from a large corpus of sentences and try the best way to learn these probabilities. Basically, you can cast this idea of assigning a joint probability also in terms of conditional probability. So we may want to assign a probability to given a history of words. So given the sentence, which is taken from a novel like Joyce, his soul swooned slowly as they heard the, and then we want to predict the next word. If we have a model which is learned from the novel corpus, then we will assign a high probability to snow. The evaluation of this task, for some reason, the equations have this more intuitive. Is perplexity, which is the negative likelihood of the actual prediction of the model compared to the ground truth, which is basically the Kullback ladder measure, which tells us how far the prediction was from the actual correct distribution, but exponentiated. So perplexity is the exponential value of this negative likelihood. The reason of the exponentiation is basically that we want to, in a very intuitive term, understand how surprised is the model to see a word given a specific context. Again, why we need this task? This is the very core of an NLP, I think, because on the one hand, it is basically what is behind the recent state-of-art models in terms of contextualized representations, which I briefly mentioned before. So the idea is that we can leverage Big Copra to learn something about language and pure sentences in a language, and then use these pre-trained models and refine them on some specific tasks, which could be dialogue systems, for example, in such a way that do not just learn from the data set we're interested in, but we can leverage a large amount of data that comes from Wikipedia or any other source that provides raw data, which is largely available nowadays. The second reason why language modeling is so important is that basically it is behind several conditional language modeling tasks. Everything you can frame as encoding from something, decoding to language, is performed through language models. If you have an author's name, you can generate a text in the author style, or if you have an image, you can generate a caption from that image. You just need to encode the image to a latent hidden representation and just decode it through a language model into something that you desire in the output of your model. And you can use it for any sort of task that has language as a output, like acoustic signals into speech transcription and so on. However, the problem is that, and I really want to take advantage of this talk to sort of repeat something that is really important to me, is that nowadays people just use algorithms like a sort of box that can be used for any language. But this is not really the case, because the fact that a model is language agnostic, meaning that it doesn't need language-specific rules, doesn't mean that the language is really the model is language independent, which means that you can apply it straightforwardly to any language in the world. And this is because, as was mentioned, we have different amounts of data for different languages. And at the same time, languages have very different structural properties. So just how multifarious is the languages in the world, I'll give you just some examples. Imagine that you make a vacation in America, and then you just walk in some areas that have not been extensively explored. Then you will find very interesting languages. For example, there's a language without the conjunction and, which is basically one of the elements at the core of, say, Western logic, and you miss that in that language. Piraha, although controversially, lacks numbers. It just has few, a lot, but no, 4, 5, and so on. Aioreo lacks tense. So in this language, you cannot express whether an action was performed in the past, in the future, or in the present. These are more like outlier, but give you an impression of like which sort of weird languages we can really encounter in the world. So we have this discipline in linguistics, which is called typology. It aims at sort of categorizing what is possible in language and what is impossible, and finding how likely are certain phenomena, and classifying languages into some specific classes. So you can imagine a sort of clock, which is an analogy made by Dixon, in terms of how languages change over time. So you have some prototypical languages that are isolating, like Chinese, that splits every word into separate morphemes, or agglutinative languages like Finnish that concatenate a lot of morphemes together, but each morpheme has a specific grammatical or semantic meaning. And then you have fusional languages like German, to some extent, that basically have several morphemes, but at the same time, a morpheme can carry different meanings. But languages shift through time. For example, ancient Chinese were more fusional than it is today, or Proto-Uralic was more purely agglutinative than Finnish, that now is surrounded by fusional languages in Europe and is sort of acquiring those properties. So this is a sort of traditional way to categorize languages. More refined ways have emerged recently. For example, there is this WALT, which is a database of typology that classifies languages based on more fine-grained properties like fusion, the amount to which specific grammatical elements adhere to the root, or exponents, which means how many categories or meanings are expressed by each morpheme, or flexivity, whether languages have inflectional classes like several conjugations for verbs or declension classes for nouns. But anyway, what is important to understand is that this variation has several effects, not just on the morphology of the language, but also, for example, in the Zipf law, which is basically a law that determines the frequency ranking of elements in function of their actual raw frequency. And then you see that languages have different curves. So some languages have quite a few words that are quite frequent, and then it has a long tail of infrequent words, whereas some other languages have basically just 100 of frequent words, and then all the others are very sparse. Also, you have a strong effect on word order. So there is a sort of correlation between how many morphology you have in a language and how free the order of the words is allowed to be, but this is very intuitive. If you can express the role of subject through a morpheme, you don't really know to assign to subjects a specific position in the sentence, like in English. Okay, this is the theoretical introduction. And now a bit more of motivation. Since we want language models, which are so powerful, to be applicable to all languages, or at least several languages in the world, we also need a sort of fair evaluation. Because what happens usually in the literature is that basically people find a sort of threshold beyond which all words are substituted by this special token unknown. And so you can find papers that report a perplexity for Finnish of 9 just because you can see that the sentences they're working with are empty, they're just sequences of unknown, and so the model is really good at predicting rubbish. Or this is Korean, the same. So this is true for all the languages that are, they have that specific sort of shape in the Zipf's law. Like here, where you have a lot of infrequent words, then you have this effect of having several words that are beyond the frequencies of even like state 5. So all these experiments that I'm going to present here are in the full vocabulary setup. So we don't discard a word. We try to estimate a probability for all words, notwithstanding their actual frequency in a corpus. So the model is a variation of, say, state-of-art, or at least until 2017-18 language models. The idea is that we have an LSTM. I don't know if you're familiar with recurrent nets, but I can present it in more detail later if you want. But the idea is that a recurrent net allows us to sort of have a compact representation of the history of a sentence and use it to predict the following words. And then previous state-of-art methods use the CNN, a convolutional neural network, in input, because this can leverage another source of information, not single words like atomic symbols, but characters within words. And we know that these characters are crucial, on the one hand, because they give us important information in terms of morphosyntactic roles of specific words. And second, because this allows us to account for very infrequent words. So, for example, inflectionally related words by this sort of convolutional layer, because if you learn about, say, a word in the masculine in German, then you can understand the meaning of the same, say, adjective in the feminine, just because it has a very similar pattern in terms of characters. However, this model has a limitation, namely that we have two sort of representations of words. One is here in input, and here we have this very morphology-based representation based on characters. But then we have an output matrix. Basically, once we have a word, we pass each character through some filters here. Then we get a character-based representation of the word and run on top of the sequence of words the recurrent network, the LSTM. However, when we have to predict the next word, we use this output matrix M. And this is the problem, because here for hand, we do not have any more the information related to characters, which is crucial, as I have just said. and it is especially crucial for languages that have a rich morphology and so very infrequent words. So we have several options here. We can either produce characters and input, rather than predicting word, we predict characters together into a word. But previous experiments showed that it doesn't really work. Another alternative, which is the one I'm going to present here, is that we can refine the word level output matrix for language modeling through morphological information that we have acquired through the input convolutional layer. So basically the idea is that we use the convolutional layer not just to represent characters of words, but also to understand which words are related to each other in terms of morphology, and then use this information to refine the matrix you see at the top. So filters that you can see on the right side column, then we can basically inspect them by activation or by nearest neighbors and see that they actually capture very similar words. So, for example, here you have some examples in German, and everything that has this sort of effect, which comes from the verb faccio in Latin, in it is sort of very similar in this space. And this is very important because we can understand partially the meaning of these words just based on the shared characters. So how can we implement this idea? Through an idea borrowed from semantic specialization. The idea is that, given these filters, we can now understand which words are similar in terms of characters to others. And we can discriminate between two sets of words that are similar and negative examples, so words that are dissimilar in terms of characters. And once we have these constraints, we can use this specific paired loss. So here you have a hinge loss, which means that up to some margin delta, we want the words with similar characters to be closer in the space in terms of cosine distance than are random confounders. And then you have a preserved loss, which simply means it's a regularization loss, which means that you want to keep the original space not so different. So you basically have an L2 distance, an Euclidean distance between the refined space and the original language modeling. So to test this model, we created a new data set because all those that we found were pretty unbalanced, meaning that they mostly geographically came from Europe. From a genealogical perspective, they were mostly Indo-European, and from a morphological, typological perspective, they're mostly fusional. So they basically represented just European languages. If you want to use a language model on anything else, you don't have a benchmark for that. So we introduced this new benchmark that basically uses some languages from all around the world that try to balance this sort of representativeness of the sample. So for example, we introduced Burmese among the isolating languages, Kannada, which is an Indian language among the agglutinative ones, and then Amharic, which is spoken in modern Ethiopia, among the intraflexive languages, similar to Arabic or Hebrew, to give you an idea. And so we created this split to test the model. The baselines to this model are the model without this component, a simple LSTM, and then an n-gram model. The n-gram model doesn't have a compact representation of the history, but rather uses a Markov assumption, meaning that you can basically approximate the sequence of words preceding the one you want to predict just by taking into account a window of words close to the target one. And the models are obtained through Bayesian methods. So these are the results. Sorry, the numbers are a bit slow, but the gist of it is that basically this method allows us to achieve state-of-art complexities in, I'd say, most languages, 47 out of 50. I don't show you here the whole list because it's pointless, but just to give you an idea, these are the averages based on the typological properties this model is mostly helpful when we have rich morphology. So agglutinative languages are those that mostly improve the performance, but you can see improvements on all languages. So of course, the improvement is still proportional to the complexity of the morphology of the language. So as I said, we see a lot of improvements, and for example, up to 950 points in perplexity for Korean. But the improvements are across the board. Here you can see a plot of the type token ratio, which gives you an idea of like how many infrequent words are present in a language against perplexity for the best performing model. And you can see that still here there's a lot we can do in terms of performance, but still we benefit a lot from this model. And also we seek some sort of linguistic explanations by correlating the typological properties that I presented you before with the actual performance, and basically it's an excellent predictor. So if you know the typology of a language, which is basically something which is known for all the languages in the world, then you can also predict very well how the language model and also downstream applications will perform in that language given a specific model. I won't give you some details here, but we also controlled for corpus size, and the model also outperforms the baselines where we have way more languages, like in the real corpus, which is not very well balanced because it contains just the languages of the European Union, but still it's varied enough to show us that with larger data sets, still the model is effective. So I'll wrap it up. So basically these are the main results. We show an improvement through this model that sort of refines the language model architectures through character-based information on topologically motivated sample of languages. If you want to get the code and data, just go to this link, basically. And yeah, I just wanted to mention that this work is done together with several people in my lab, so I wanted to give credit to them as well. But yeah, wrap it up. Thank you for inviting me, Rasa.
So, does anybody have a question? Or no,
Oh.
maybe you go first.
Is it published and can we find it?
I'm sorry?
Is your work published?
The papers were, sorry, for some reason the size of the font changed, but the references are well, doesn't work anymore. Here. No, but I can give you like reference data.
Somebody else?
I do have a question, maybe.
Yeah.
Okay, so you mentioned something about trying to predict on the character level not working so well.
Right.
Can you just briefly elaborate on that?
Yeah,
Because
sure.
I think there is somewhere trying to have a character level LSTM on the output
Right.
Android.
Yeah, exactly. It's I'll show you the work exactly. Yeah, because as I said, like the idea is that we want to find a way to, okay, I missed it somewhere. But the idea is that you want to find a way to use character level information in the output, right? So what you can do is, rather than predicting words, you can predict characters. So you predict a series of characters, and then at the end you predict a space, and so whatever came before, you just bundle it together and check whether the word that comes out from this prediction actually matches the gold standard word. But the problem was that with equivalent parameters and comparable settings, this way to predict the next word kind of perform really bad compared to actually predicting bare words, not even without this additional component to refine the space, but just with pure LSTMs.
Is that due to a restriction in the sort of memory that the decoder can keep track of, because you have more time steps when you're doing it?
Exactly, yeah. We know that LSTMs, although in principle they have gates, so they should be able to learn even long distance dependencies, fail to actually capture the entire history before, say, the next item. So if you have character at that granularity, maybe you miss the semantic information that comes from previous words. So I think that's part of the problem. So I think, yeah, you had a question as well.
Yeah, it was also on this slide. So, I mean, 2 parts. One, you said you get these for the attract repel heuristic. I wasn't quite clear on where you get the positive samples from, like what should be close. And then, if you could just talk me through again, what you do. Do you like use it to bias the decoder, or what do you actually use that information for at the end?
So basically, the idea is that given the input filters, we can get a character-based representation for each word. So at each epoch, basically, we estimate a character-based representation for the entire vocabulary and get the nearest neighbors from each word to get basically positive samples. And then negative samples are just sampled randomly from the vocabulary, excluding the nearest neighbors. And so basically, you learn to attract words that are actually very close in the space. They are actually your nearest neighbors. And leave. The way we inject it is simply, let's take the output matrix, which is basically, imagine that you are at the top of the LSTM layer. So you have some hidden representation for a word given its history. Then you want to map the dimensionality of the LSTM. This is just a linear mapping into the dimensionality of the vocabulary. And then you have a softmax layer that takes the basically squashes the probability, and you get the argmax, which is the actual prediction. But before that, before we actually map the hidden representation into the, say, probability distribution over the vocabulary, we have this matrix M, which is what we actually want to refine. So we want to check how a sequence corresponds to some specific words. And that's where we inject this information. So we take that space, and we use the attract component of the loss to put closer the words that are similar in character, but for the rest of it, we keep the M as close as possible to what is learned through the epoch by the language model itself. Hope it was okay.
Any last questions? No, okay. So you can catch up with Edoardo after that. First,
sure.
Thank you so much.
Thank you.
Cool. I will just mention something very quickly, which is after all these slides. Well, there's some. Yeah. So actually, Rasa is hiring. If you're interested in joining the team, like you can just go to our website rasa.com/careers, and you can find out what we're looking for, or you can just text us at hi@Rasa. Thank you so much for coming. There's some more beer, club mate, beer left, and then yeah, you can talk to the speakers. Thank you.
Sure.